So, we continue with our discussion on multiplexing, and this is the diagram we tried to understand in the last class, okay, where the basic idea was, as an example, to show how a 24 speech telephone grade speech signal can be combined after processing through low pass filter, and then can be combined to form a multiplex data output which would be launched to the physical channel. Okay, and the corresponding scheme for the receiver side was something like this, where from the channel we would get this multiplexed data, okay, and then it would pass through the corresponding PCM decompression unit and the PCM decoder. The output would be, I mean, in the ideal case, would be delivered to the respective desired output points, and towards that a very important feature was synchronization of frame. Okay, so there will be some kind of frame synchronization unit coupled with this box over there, so that ultimately the message speech signal reaches the desired user, not to anybody else in the process. So we'll go somewhat quickly today, like we calculate a few some simple calculation like the number of bits per frame. We talked about frame accommodating 1 byte from each user, okay, and there being 24 users, one can say that the number of bits per frame will be 8 bits, which will make one sample equivalent in the digital domain, okay, 8 bits per sample into 24 samples from 24 users. That means in one frame there will be at least one sample from each user. Okay, in a very general case, not in this standard, in a very general case there may be multiple samples from a particular user, okay, depending on the kind of service that he is using at the moment. But anyway, for this standard there will be one sample from each user in one frame, okay, and then the number of bits to be accommodated in a frame is 8 into 24 plus 1 sync bit for synchronization. We call it as a synchronization overhead. These additional bits will put here and there for some specific reason, and all these are very important, very necessary to ensure that the signal goes in a formatted manner and they ultimately can be disseminated for the respective users. There is no mismatch in between this process of multiplexing and demultiplexing. So, the total number of bits in a frame is 192 plus 1, that is 193 bits per frame. Okay. And you remember perhaps that the frame duration is 125 microsecond, it has to be really, okay, and hence I can calculate the overall bit rate after multiplexing. So, before that, let us have a quick look at the frame structure. Perhaps you understand by this time really. Only thing is that this location, the frame synchronization bit or frame overhead bit, 1 bit, is usually put at the beginning of the frame, okay, and then these are individual slots for 1 bit, okay. So, I have shown here 8 provisions for 8 bits, and I am allocating this portion of the channel of the time frame to channel 1. So, similarly, the next slot of 8 bits will be allocated permanently for channel 2, and like that the last slot of 8 bits will be allocated to channel number 24. So, the first frame will consist of the first samples from each user, okay, following the frame overhead bit f, and the total duration is 125 microsecond. And you may wonder how by using only 1 bit one can synchronize the frame structure when they are received. Okay. In fact, it is not only through 1 bit. The frame synchronization actually is achieved by sending a sequence of 12 bits as per this T1 hierarchy, T1 standard. The frame synchronization is achieved by sending a specific sequence of 12 bits, okay, through 12 consecutive frames. So, if this frame is the first frame, this first one goes in this slot, the second one goes in a similar position in the second frame, this 0 goes in a similar position, that is in the first bit position in the third frame, and like that. so that we know that over a 12 frame period there will be a sequence, this specific sequence, okay, if I catch the first bits of the frame. Okay. So, in the frame synchronization unit in the receiver, you have to have a circuitry which will look for this particular sequence, and you should suggest me how this can be achieved really.
So, sir, one thing is,
yes,
sir, like when a frame comes to the receiver,
right,
so the receiver gets only the first bit. So that for the particular
this
frame,
bit,
this bit, the F bit, so for the particular frame, so only that bit is the one causing synchronization. So because that frame has to be accepted by the by the receiver right then.
right.
So what is the user having a 12-bit character size? Why do we need 12 characters? 12 bits.
See, if you think a little bit, I am giving a rather simple picture at the moment, okay, just as an overview. If you think a little bit about the timing problem, lack of synchronization that may occur at the receiving end, see, if you think from cold start, that well, the transmitting end, the multiplexer has suddenly started sending frames, okay, and the receiver has been switched on just at that moment or even sometime later. You really do not know even whether this is the first bit that you are receiving, okay. Okay, you even do not know to a very fundamental level whether the clock that you are using at the receiver end is in synchronism with the transmitter clock. Okay, so there may be many issues of uncertainties. In fact, we are not talking about a clock synchronization at the moment really, we are talking about frame synchronization, assuming that there is ideal synchronization in the clock by some other technique. Okay. So, then coming to frame synchronization, there should be several issues again, like one has to detect the beginning of the frame. Okay. One has to also know by the frame structure, of course, what is the end of the frame, because after that the next frame starts. So, detection of this beginning of the frame is of paramount importance, and that you can never do by using a one bit, only one. See, if the first bit is 1, if you receive the first bit as 1, how do you know that this is the starting or beginning of the frame?
So we can have a set protocol like initially
Like
like getting point. We can't say whether this is in the data or
whether this is the data or whether this is a sync bit, you do not know.
so do we have to wait for 12 frames before
Yeah, that's the point really. Initially, before this frame synchronization is achieved properly, the received data may not be fully reliable. Okay, fine, because you need this 12 frames to first get a first hit that yes, this sequence has matched. And there again, if you just think a little bit about the problems that the channel, physical channel may cause, etc., instead of an exact 12-bit match, you may even land up with an 11-bit match.
so the point is also that like even if instead of getting the frame bit, I get a data bit, I won't be able to distinguish even then.
Pardon?
Like instead of the first one,
Right?
if I get the one I'm getting from the data, I still
Right.
won't be able to distinguish whether it's coming from the frame or from the data.
Yeah, you cannot. So, if you receive only the first frame, you really do not know whether, I mean, when the frame started.
Sir,
Yes.
during the starting of the communication,
Right.
we are assuming that we are catching the receiver has started before the signal has been.
Okay.
So initially we can send a particular kind of code
Sequence.
like that we are going to start the data
Right,
transmission.
right.
It not necessarily be just a single bit frame synchronization.
Right, right.
In the starting we can send a long bit of sequence.
That's
Just
what
to,
is a very good suggestion. It is usually followed when the transmission is not really continuous. Okay, it may transmission may be intermittent, and once in a while you can send this kind of synchronization sequence ahead of transmitting the traffic or the data really. Okay, that is done in many other systems, but usually if you think this multiplexing scheme, as I mentioned, I think is was primarily designed for telephone system, where this multiplexer output will be almost continuous. Okay, because the multiplexer output will be all the time transmitting this multiplexed output. So, in fact, this issue of starting from cold really is not there. So, once it has started, see, the exchange has to be active always, because you do not know when you will get the data.
but there would be time when we have to send some another kind of data, like we have changed, we have to connect this, we have to switch over to another particular line, like this connection has been broken, and
That is not the job of this multiplexing demultiplexing unit, as I mentioned briefly. That is the job of switch beforehand really. The switch ultimately generates these 24 inputs which are to be multiplexed. that is what is called as signaling. Okay, I'll mention about signaling really. There is a provision of signaling in this frame format itself really, so that even before the speech data goes, okay, the number that you dial will also go through the similar frame structure really.
So every frame structure has to be defined. Like that
Yes.
particular frame
So
structure.
he is coming to the point really. It is very important to define the frame structure and ensure that the frame is understood completely, and this definition should be uh, done such with a minimum amount of overhead, because the line is going to be active really. Okay, in fact I was guessing that somebody would say, why sir only one bit you are using for one frame, why not use a good amount of say all this 12 bit, why not I put in one frame itself, so that in one frame I can get a synchronization signal. Okay, the whole standard is a compromise between the two really. Okay, on the one hand this kind of multiplexing demultiplexing unit will be operational continuously, okay, and not much variation in the clock signal is expected. The clock that is to be used will be highly stable, because this is a situation where you are talking about taking 24 users data at a time. Okay, so it's become the whole information is now very costly. Okay, so assuming those things, now you'd like to minimize the overhead, because instead of sending all these 12 bits in one frame, if I can operate my multiplexing demultiplexing unit reliably by sending one bit, then I save 11 bit positions really. I can accommodate one more user there. So there is a balance between the various conflicting requirements, okay, and this standard so is good for telephone communication system, may not be good for other applications. Yes.
So is there any reason for using 12 synchronization bits?
Again the same thing really. 12 is a number which is not too large. Okay, now if I would have used if a larger sequence would be used, you can guess now, as he was hinting, that one has to wait for more number of frames before you get a hit, before you really detect this synchronization sequence really. So you would have to have a large amount of buffer. Okay, not only that, speech, if it is delayed too much really, can be understood. Okay, you can feel that, so that is not to be done really.
Sir,
Yeah,
the buffer will cause a delay.
will cause a delay. Yeah, so that may not be, that should be objectionable in some cases. So some buffering, limited buffering is fine, and mind that this buffering, this kind of synchronization is to be done once in a while. This synchronization is not necessary when you start speaking and your signal goes to this multiplexing demultiplexing unit,
How can, like, if the initially you have started buffering the signal,
right?
then in intermediate stage, how can you remove that? Eh, how can you get rid of the buffer?
Okay, let me simplify your problem. His problem is that if I have allowed buffering, like for this 12 bit sequence, I cannot declare that I have acquired a frame till I get 12 such frames, isn't it? So his point is that if I am fortunate really, I may not get even the first 12 frames at exact match of 12 bits, okay, if the channel is too bad. But for telephone system, the channel should not be too bad. Okay, so it should usually be obtained in a size of 12 frame duration. Okay. So there is a buffering delay. So his point is that if there is a delay already involved, how do I remove this delay? The point is that please note that, as I said, usually before you speak, you signal, you dial a number. Okay. So far as your speech signal is concerned, even if 8 of your slots or 12 of your time slot is wasted, is delayed for dialing, etc., your speech does not suffer really. You may get the ringtone a little bit later. How does it matter? Your active speech has not yet started. So this scheme works well. Okay, it's shorter bit duration. Why not? Larger than 12 means more delay in the process really. Okay, if it is not necessary, why do you go for that? A shorter sequence of say this 5 bits or 6 bits, should I have used that? Because then it would be more probable that such a sequence matches with the data traffic.
How can we make sure this doesn't match with any data?
Yeah, in fact, so some study was made and it was found that such a sequence is rather rare to occur. So it has been decided like that. Okay, so as I said, really, a lot of study, etc., have done it before the standards have come.
So basically, once we first synchronize the frames, then we don't need to do them every time.
No, it is not necessary. Okay, but it's good. It's good to keep track really, okay, because you do not, suddenly there may be some glitch. because of some lightning or some such problems, depending on the link connecting the exchanges. One at a time. Yeah.
Expected sequence of the bits are 11016.
Right.
And initially we get something totally different, 00 from the data.
Right.
So how do we adjust?
Can you repeat the question? Is this question understood by all? Yeah.
So initially we have received say 0011 at the sync bits. So we have been actually sampling the data.
No, the point is that at the receiver, you will be receiving a frame like this, where you should tap, you should consider this first bit position for all 12 frames after you have received. Okay. Then if you find a hit, you know that you have cut, you are really at the first position of the frame really. Okay. If it is not, then you go slide in a parallel fashion to the next bit positions. You will find a match. You should find a match. Okay, unless there has been a lot of errors in the channel. Is that okay? Yes.
So what happens if all the 12 bits don't match? Suppose only 10 match.
Think about. Yeah, it's a possible case really, but it's not so frequently likely. Okay, but just tell me a little bit for our interest. Why should it happen? It can happen.
So because of error
Because of error in transmission. Yes, you may not get a match every time really, but the point is that once you are synchronized, assume that this is not a very costly issue, because once you are initially synchronized and then on each frame you are trying to verify that yes, I am in synchronism, then a occasional miss is not so costly, because after one frame again you will find that it is matching. So you can say that okay, that was an occasional deviation because of error. The problem is more costly if this thing happens right at the beginning, when the whole thing is being initialized operation really. Okay. So if it is found that okay, it's not matching in 12 frames or 13 frames kind of thing, then one has to get back into the physical link. The link is not very stable that way really, and there are standards for what to check and what should be the values of the received signal, etc., etc. From that, attention is diverted there, so that the link is made of better quality and you get back a synchronization within 12 frames. Okay. Yeah.
in the telephone system, generally we have the link established before the actual speech transmission starts.
Yeah, in a conventional telephone system, it is like that. Your path is established beforehand.
Established before, and then the actual speech signal.
It is known as, the system is known as circuit switched network. Yeah.
So in this case, if in the initial process, when this signaling is going to be there, circuit switching is going to be there, at that time we need to do this frame synchronization.
In fact, as I said, this frame synchronization is not depending on a particular user's call initiation. See, if I just get back a little bit again, the frame is generated at this point, which is not at user's premise. You may or may not transmit. You may or may not dial a number really. If you are dialing a number, you will find a frame already going with somebody else's signal. Okay, and you will be given a slot there, so that your data will get in there. See, the frame is always on. Take it that way. Frame is always on. You want a time slot in that frame. Okay, so you are dialing. Fine. If actually some time slot is available, you will be accommodated a time frame, a slot of 8 bits. Okay, your dial data will pass through that. Okay, so you are not triggering a need for synchronization as an individual user.
So the need for synchronization in every frame will be necessary, because the initiation of a signal can be
from the user side. Yes, but this telephone system, that means from the exchange onwards, okay, there is a multiplexing unit always on with 24 time slots available. Yeah.
Only after we have synchronized, only after we get those 12 frames of synchronization.
A particular.
So basically synchronization is to see which data has to go to which switch, which destination.
No, not really. Not really. The purpose of synchronization is to ensure that, okay, the signal from this input port of the multiplex, okay, is diverted to the output port, the corresponding output port in the demultiplexing unit. So the synchronization is for this multiplexing, demultiplexing operation only. Yeah.
That means only after getting those 12 frames,
right,
then appropriately connect the switches to the various.
Right. So, I can say that irrespective of whose signal is coming to this input port 1, the synchronization operation in the demarks has to only ensure that that data which is being tapped from port 1 is delivered at port 1 prime here. Data which I am getting from port 2, okay, has to be delivered to this point irrespective of where from the signal has originated. That is the job of the switching.
Subsequent routing and all will take.
Yeah, one at a time.
Checking for the synchronization happens every 12 frames, or it is like
For the first 12 frames, you get a confirmation that okay, the frame has been acquired. Okay, then on each frame you go on checking because you know the previous 12 bits, because the sequence is fixed. You know the corresponding portion. See, if you have received this full sequence, you know that the next bit is going to be 1. So if you really get a 1, you know that there is frame synchronization is maintained. Yes, please.
that is an extra information. We would be requiring more bandwidth than what.
Yeah. So that's the point you are hitting again, is that that's why this kind of additional bits which have to be there, okay, for proper operation of the whole scheme is known as overhead bits, okay, and we would like to minimize it because we will see shortly that this kind of overhead actually adds to the bandwidth requirement somewhere here. So there is a tight estimate which is made about what is the minimum amount of extra information or group of bits which must be added. Yes, so it is not arbitrary that 12 bits were chosen. Okay, 12 bits were sufficient to maintain the quality, okay, and providing more number of bits would be, yeah.
Even the address information where it has to be delivered.
It has got nothing to do with the address really.
No, not this one. Like if we would be sending one particular frame, that the input from the L1 S1.
I'll mention about the addressing unit just a little bit later. Okay. Any question to this? So the overall bit rate you can calculate is 193 bits per 125 microsecond. So it's 1.544 megabits per second. This figure you should not forget. Okay, as per T1 multiplexing structure. Okay, when 24 channels are multiplexed, the overall bit rate is 1.544 megabits per second. It is just a little bit more compared to 24 into 64. Okay. So it is now easy to calculate that a 12-bit frame synchronization code repeats every 12 into 125 microsecond, that is 1.5 millisecond. You can see that a group of 12 frame needs only 1.5 millisecond. So that frame synchronization code, the 12-bit code repeats every 1.5 millisecond. It's not a large time at all. Okay. So that the frame synchronization bit rate, if I calculate, is 667 bits per second. 667 bits per second. Yeah, it takes 1.5 millisecond to receive this full 12-bit synchronization code through 12 frames. So if I now talk about the average rate of frame synchronization bit, it comes out to be 667 bits per second. Okay. Now that issue of associated signaling, what he was going to ask really, I stopped him in between, is called as channel associated signaling. Before your actual speech signal goes, okay, you dial a number, okay, you get some ring back, and then you start talking. After your call is over, you put the handset onto the cradle, that initiates another call termination signal to the exchange. Yes, please.
Don't access bit rate 1 bit for 125 microseconds, not for 12 frames.
Pardon?
So each frame is passing only 1 bit.
1 bit.
1 bit per frame is access bit you're passing.
Right.
8 kilohertz. 8 kilobits per second. Okay.
1 bit per frame.
Per frame is what you are transmitting.
And what is the frame rate?
That's same as frequency. 125 microseconds.
Right.
Kilobits per second.
Right. So this is not 667 bits per frame. This is 667 code, full code per second, not bits per second. Yes. This 667, you get the code, full code, 12-bit code, 667 times per second. Because per 1.5 millisecond you get the full code of 12 bits. Okay. So in 1 second you get 662 times this full code of 12 bits. Sorry, thank you. Okay. So, for call initiation, that means dialing, etc., call termination when you put your handset on the cradle, okay, and address of called party, the number you dial, etc., all these are necessary signaling operations which have to be there before your speech communication is successful. Okay. So, all these things are called signals, and they are signaled using the LSB, the 8th bit, once every 6 frames. Does that make sense? You just see, as a user, okay, what you will get in a frame is a time slot of 8 bits. Okay, fine. Now, when you dial a number, the number has to be communicated to the destination, and we want the exchange has to find, the telephone system has to find whether the number is engaged or free. Okay, so depending on that, you will be given back some ringtone, okay, or engaged tone. Fine. Now, this kind of information, the moment you dial, you get a time slot for 12 for 8 bits per frame, and in this 8 bit, now if you think of putting level to the bits, really MSB, second MSB, etc., up to LSB, then the LSB is used. Okay, the LSB, that means per 1 bit only the LSB is taken out for this kind of signaling. Okay, in fact, if you think a little bit, there is a need for signaling before the speech starts. Okay, there is a need for signaling after the conversation is over, and on some cases there may be a need for signaling even when there is conversation, in some special cases really. So, usually the signaling is before the active, I mean not signaling does not disturb your conversation. Okay, that is what is ensured. So, what happens is that the 8th bit in the LSB is allocated once in every 6 frame for this kind of signaling. Any signaling will occupy the 8th bit, that is the LSB. Now, if you think about the 8 bit representation, the LSB as if is going to be affected. It may not mean much to the distortion of the signal really. In one sample, the LSB value may get disturbed. Instead of the speech value, the corresponding signaling value will go through that. Yeah.
Before you started talking,
Yeah.
like let's say I'm dialing the number. This number has to be sent to the receiver.
Right.
And then when you go in the LSB in every 6 frames, I'm being very inefficient because in that time I'm not using the other bits also. I mean at all.
Right.
So why not use all the 8 bits to for processing the number I'm dialing?
Yeah. In fact, again, I mentioned only about a few signalings. There are certain other signaling types really. Okay. If and the signaling requirement is not the same really. Some signals are needed very slowly. Okay. But here, as he mentions very, I mean reasonably, that well, the whole number should be sent using all 8 bits. Okay. Yeah.
So that cannot be done as such. So
Yeah.
if you are assigning the whole frame,
No, not whole frame. That full 8 bits for one user.
you are using out of 12 frames, one frame you are using.
No, no, not frame. One byte for one channel. If I get back to this, see this full frame is allocated to 24 users. Okay, this is for the first user. Okay, instead of this, let me call this channel 1 means the bit allocation for one user.
So that means the
In one frame you will get 8 bits.
Yours, the 8 bit
Yes.
of every contains the respective address.
Right.
So that means the whole frame has been occupied by only addresses.
No.
If all the 24 users have simultaneously dialed, well, it may happen. Is it not?
8 bit is given the address for the associated
For signaling, yeah, for any kind of signaling. But no, remaining 7 bits, if there was no active voice, the remaining 7 bits go unutilized.
Sir,
Right.
each bit will come every 6 frames at the 8.
Yeah.
What are the remaining 7 bits in that byte?
They are not utilized for signaling.
So what is it used?
Okay.
They are just empty.
So during signaling, okay, as I said, signaling will take place before you start speaking. Signaling will be there after you stop speaking. So there will be need for signaling even in between, really. So, pardon?
It's a kind of status, whatever the line status.
Many other issues are there, really. Okay, and there may be some emergency needs as well, really. So this uniform style at least ensures that even if there is a need for signaling during active voice period, the signal is not affected much. Your objection, I hope I have understood, is that why we are leaving a few bits void really. Okay, the point is that one should also see that if there are different signaling rates, one should not entertain a very high signaling rate for one kind of signaling, while for other kind of signaling the rate invariably is much smaller really. That leads to different kind of problem. See, if there is one signal handling unit somewhere, then it has to operate very fast to take care of these fast signals, while it can operate very slow for taking care of the other kind of slow rate signaling. Okay, sorry, that's not a good approach in the design of a system ever really. Even for multiplexing, it is ensured that the input signals from various users, they occupy either the same bandwidth or relatively similar bandwidth. Multiplexing a video signal along with a voice signal is a very difficult thing to do in hardware, because the video signal rate is much higher compared to the voice signal rate. So there are practical issues really. Okay, so and this, even if these bits go unutilized, it doesn't matter much. Okay, in this basic scheme, of course, there are more advanced multiplexing schemes where even this much of unutilization is used, but not usually for voice kind of applications, for voice data integrated applications, where you can send non-real time of services like data, etc. Okay, so this is the beginning of this example that I took is an old example to understand the basic issues. Now the individual questions that you will have in mind, keep them, they have got the relevance really, but not in this old style format at the moment. Yes, multiple, yeah, one at a time. Yes.
You have so every six, suppose someone is dialing a number, so that means the multiplexer, one is now has passing that line coming from his telephone.
Right.
So then why are we sending the address every 6th frame? So that means it will take about 36 frames to dial a.
So the frame rate, you can see the signaling rate is 1.3 kilohertz, 1.3 kilobits per second. It's not too bad really. See, signaling every 6th frame. So the signaling rate is 1/6 of the frame rate. Okay, 8 kilosamples by 6. It is 1.3 kilobits per second. Is that too small? You have to send only some 10 digits, isn't it? It doesn't take much time.
When the multiplexer is dedicated to my line, why not every frame or every?
That adds to hardware, that adds to problems upstream really.
Basically, more buffering would be required.
Pardon?
More buffering of the data would be required. If we are using
If we are sending
As per this scheme.
no, not this specific. If we like after 12 frames, we are getting to the signal. Like in the starting of the frame, we need to show 12 such frames and then get the word line signaling information.
See that initial buffering of 12 frame is not at all an important issue. You better consider that the multiplexing, demultiplexing, they are already operational. Frame has been synchronized. Okay, now this line is available for the users. So let there be data from various users, they will be multiplexed. And there again, before they send actual active information, okay, they will dial something. So that number has to be again communicated through the same frame format. And there we are saying that okay, that those bits will be taken at the rate of 1.3 kilobits per second. It's not a very small rate, but it's sufficient. Okay, for that, yeah.
One big LSP we are using for handling various kinds of signals.
Right.
Like calling, switching,
Yeah.
dismissal.
Yes.
So is it sufficient for all this?
Because I can see, I can calculate the bit rate is not very low.
No, the bit rate so a group of those LSPs are used for one particular kind of signal to decode which signal actually it is specified.
Yeah. So over a few frames only, okay, one can identify that okay, this is the dialed number. This is the dialed number. Okay, so that number has to be connected. That can be understood. Okay, so the signaling, yeah. No, this is for individual user. See, for one user, okay, he gets 8 bits in a frame, okay, and then think about the LSB, and every 6 frame one LSB is used for this frame, this signaling purpose. Yeah, there was one question. Yes.
So my question was like, if we we are dialing a number, say, and we are transmitting the number.
Yeah.
Say the digit 9, sir. So that will be 1001 or something.
Right.
So that will be like 1 will be transmitted in the LSB of 1 frame, and then after 6 frame a 0 will be transmitted.
Yes, like that.
Something
Like that. Yes, you are correct. Yes. Louder, please.
The frame synchronization bit is also present as a signaling bit, isn't it?
No, the frame synchronization bit is the first bit. So this this signaling bit is within that slot of 8 bits per channel. Say if you talk about user 1, if user 1 is dialing a number, user 1 if this is the LSB, this position will be utilized in the first frame, then in the 7th frame, like that. Yet the frame synchronization bit is always present. These in between bits, they go unutilized if there is no active voice. For dialing etc., they may not be utilized, but that's for a very brief duration. So your concern is well taken, that okay, in this scheme it's not the most efficient, if I may say so. Okay. Yes, so the hierarchy really didn't stop with this T1 architecture, but that was good. It served the purpose very well for several decades. Even now it is used. Okay, but when technology is available, now people are more concerned about increasing the efficiency, reliability of this frame formatting and designing, etc. And there are many other schemes available for that. Okay, one of the most efficient scheme is known as statistical multiplexing, which we will not discuss. Okay, yeah.
Sir, in this also there will be a problem of synchronization because after the 6 frames that we are passing,
The problem of synchronization is no more there because the frame has been synchronized.
after the 6 frames that we are sending,
Right.
we do not know in which frame the signaling data is present.
the bit of the frame.
Right.
The signal is present.
Okay, that I didn't explain here really. It is so his point is that because the LSB is being used, how does the demultiplexer unit know that the LSB now is being used for signaling data really? Okay, so there is associated signaling format. Okay, that is not the part of this main story here, so I am not talking about that, but it is taken care of really. Before signaling starts really, again some sequence is sent so that the other end knows that okay, now there will be some signaling information. Kind of.
Can't we use the frame code itself?
Frame?
Frame code.
Oh no, it should not be used.
We can use this.
No, you can see. This is used specifically for frame acquisition to synchronize the frame.
The same purpose of it.
No, may not. No.
Like we can
See, there is no dearth of sequence. Let me tell you that. Okay, there is no dearth of random sequences. Okay, which have got good autocorrelation properties and very poor cross correlation properties. So getting a sequence is not an issue. Okay. So I go to the next step. Okay, that's of hierarchy. Okay. So after T1, where the output is at 1.544 megabits per second, which contains basically 24 voice users information with some little bit of overhead. Okay, in the next level of multiplexing, this is that PCM multiplexer. With 24 voice users, the output is at 1.544 megabits per second. At the next level of multiplexing hierarchy, I am noting the multiplexing unit as M12 as a multiplexing unit which is taking input from the previous level 1 T1. It is taking T2 and is going to generate taking T1 and it is going to give what is known as T2 at its output. So 4 such T1 outputs are taken, each at 1.544 megabits per second, and these 4 channels are now multiplexed here in M12 multiplexer. Let me write, it is mux M12. There is an interesting issue here. When you think of multiplexing these T1 carriers at 1.544 megabits per second here in this mux. Usually quite stable oscillators are used at this level, PCM multiplexer level, where 24 voice channels are multiplexed. Okay. But when you look from this multiplexing side on the input side, where 4 inputs are coming, 4 T1 inputs are coming from 4 PCM muxes. Usually it so happens that these muxes, they are at physically different locations. These muxes may be located in small exchanges. Each exchange may have one such PCM mux which can multiplex 24 channels. So the second input may come from another small exchange which are physically at different locations. So they have got independent but quite stable oscillators for their timing signal generation. So the inputs at this multiplexing stage may not come from the same place. That means these inputs may have been generated using independent though stable timing generators, and hence there may be little bit of variation in the bit rate. Okay, somebody's clock here may give exactly 1.544 megabits per second as in synchronization with the master clock here. Okay, for some input the clock may lag a little bit, for some input, another input, the clock may lead a little bit, so that the actual time over which you get a frame may not be exactly 125 microsecond. Does it make sense? Okay, there will be little bit of mismatch. In one frame you had 193 bits, you may receive 193 bits in this line, say exactly at 125 microsecond, just as an example, as a base. Whereas at this input you may get 193 bits not at 125 microsecond, maybe at 124.9 microsecond. There may be little bit of variation. Okay, but that should not disturb, that should not at least injure the information from individual users. So this incompatibility in the independent clock rate is adjusted or taken care of in this multiplexing level. Okay, and the operation that is usually carried out is known as pulse stuffing. What happens is that you go by your master clock, okay, and then if you feel that okay, for some you are yet to get 193 bits, you have to wait, because you cannot leave somebody else's bit really. So wait till you get 193 bits from the slowest channel, okay, but by that time you have already received 193 bits from other channels, so they are in the hold mode really. Okay, so you add a few bits there, so that you can say equivalently now all the 3 inputs have been arranged to have occupy the same time. So you add some extra bits, so that their duration which have come earlier, which have come faster really, they also now take 125 microsecond. So make them looking uniform so far as the time duration is concerned. Okay,
That will distort them.
it will not distort, you are adding some extra bits which are meaningless bits to ensure that the frame period is now aligned to 125 microsecond for each input as if.
But won't it disturb the frame format? So won't it disturb the frame format? I mean, like the frame won't be uniform.
So what will be done is, at the same level in the demultiplexer, and this level 2 demultiplexer, the demultiplexer will take care of this pulse destuffing operation. The idea is that not anywhere before this, to reduce the complexity of these individual multiplexers, okay, they have been allowed to operate with moderately stable oscillator, because maintaining a stable oscillator is costly. Okay, again a compromise, and design compromise really. So this pulse stuffing operation is done at this mux level, and the corresponding destuffing operation will also be done at the demux at level 2.
So why to add extra? Just keep it hold.
that perhaps will distort the frame structure. Think a little bit. Think a little bit. Okay, we'll discuss really. If because you have already received 193 bits, okay, but it's yet to be 125 microsecond. Okay, your frame duration is 125 microsecond exactly really. Okay, sorry. So if you start taking out at 125 microsecond, okay, so you have these bits, you cannot really go for any further reshuffling there. Any major reshuffling, rearrangement there would again increase the processing cost here in this multiplexing level. So simple way is to add a few bits there, stuff a few bits and continue, let it continue with a few more bits. So the timing alignment is not disturbed in the process.
So that means you have changed the frame.
No, frame duration is not changed. Frame duration is 125 microsecond.
So then it requires buffering.
Some buffering will be necessary. Yes. The minimal buffering is accepted. Huge buffering is not to be encouraged. Okay. Lot of processing here, bit manipulation is to be avoided.
So if in the whole process we look out, the particular frame size would be around 125 microseconds. Whatever like the sequence
It's around 125 microseconds.
it would be around 125.
Right.
So what we are concerned with, like it's exactly regarding the 193 bits. It's not about the time which we are more concerned.
It's a time which is more, which is of importance because it is ultimately a time division multiplexing format which we are following. Time is of most importance. Bit slot, okay, because the whole multiplexing is done on the basis of timing. So time is very important issue. Okay, let me complete this thought at least. Okay, so this operation, minimal operation I will say, not a very involved operation, is carried out so that the frame timing is not disturbed from this point onwards. So that the overall rate is not simply 4 times 1.544, okay, it's a bit higher. How much is that? We can see that at this level marks 17 bits are added for synchronization and pulse stuffing. A provision for 70 up to 17 bits is used, okay, for pulse stuffing plus synchronization. So there is one level of synchronization at each frame. There is another level of synchronization at each level of multiplexing. Okay, and the additional feature that will come in is this pulse stuffing. On the whole, 17 bits are provided. I am not going into how these 17 bits are used. Some are left for pulse stuffing, the rest are used for synchronization purpose. So the number of bits for M12 frame now is 193 into 4 plus 17, 789 bits. And now by calculation that okay, every frame takes exactly 125 microsecond, that is 8000 frames per second. So the overall number of bits is 6.312 megabits per second. This two output at this point will be at the rate of 6.312 megabits. Okay, I mean somewhat similar is the story upstream. At the next level of multiplexing, marks M23. Okay, it takes 7 such inputs, T2 inputs, each at 6.312 megabits per second. But there again, now I can imagine that these inputs may be even different places. Okay, so now their oscillators may not be synchronized, and hence the provision for pulse stuffing should be there. And ultimately, the 7 such channels multiplex outputs are multiplexed here at this level. So the overall rate will be close to 44.736. It is 44.736 exactly after including 69 bits as overhead, as pulse stuffing for pulse stuffing and synchronization. So that the overall bit rate now is per frame, number of bits per frame is 789 bits, okay, per T2 frame. There are 7 such T2 inputs plus 69 bits as overhead. So the total is 5592 bits in the same duration of 125 microsecond. So that the T3 line rate is 44.736 megabits per second. Okay, I'll stop here only after telling you that at the next level of mux 34 M34, 6 such T3 inputs are taken, each at 44.736 megabits per second, and then 720 bits are used as overhead in the form of synchronizing bits and pulse stuffing bits, so that the output rate is 274.176 megabits per second. Okay, this stage is not very important, because in the present scheme really, which is a little bit of different, from this T1 series etc., this stage is not defined really. Okay, nominally it's up to this level 3, where T3 you get. Okay, so let me stop here today. The story is incomplete again, so we continue for some more time the next day. Yeah, I was thinking of discussing a fresh issue, a fresh topic next day. Yeah, one at a time. Yeah.
So number of different channels for the different multiplexers.
These numbers, they are fixed. That's a part of the standard. Yeah. M23, M12 has got 4 inputs, 4 T1 inputs. M23 has got 7 T2 inputs. M34 has got 6 T3 inputs. Like that. Yeah. Previous slide for calculation. You essentially have to remember the additional overhead bits. Okay. 17 from T1 to T2, then 69 from T2 to T3, and then 720 from T3 to T4. Okay. Then we'll briefly discuss about an ITU T standard briefly before taking up the next topic. Thank you very much.